All right, so good morning, good afternoon, everybody. So today I'll be discussing some of our own ongoing work at the University of Manitoba, and that is related to incorporating topology and the topological complexity into a multi-layer perceptron. So just as a quick overview of what exactly we focused on with regards to multi-layer perceptrons. Multi-layer perceptrons form the backbone for many of today's deep learning frameworks. This is the sort of idea that we have a set of neurons. Each neuron is a sum of is a weighted sum of the previous hidden layer, and this is the way that we sort of parameterize a model. And then what we do is we sort of learn these weights that are relevant in terms of with regards to sort of making a prediction. So a model is pretty much just looking at a set of training and testing data, and it's parameterizing this model based on the training data and trying to find out which unique combination of weights is most likely to correlate to the prediction that we're looking for. So we're parameterizing and then we're adjusting these weights. And a lot of these deep learning frameworks in some way have this idea of a multi-layer perceptron built in, at least implicitly, as time has gone on and as deep learning frameworks have advanced. And the thing is, during training, these models are creating, sort of in the background, these non-linear decision boundaries. And it's doing this in order to separate the data. So what it's doing is in each layer, it's sort of producing a linear projection, or sometimes people call it mapping, whatever it may be, but it's sort of projecting lower dimensional feature space into higher dimensional feature space when you sort of increase the number of neurons in these hidden layers. And then the model is sort of learning these high dimensional representations. And then by definition, when it's sort of propagating through the network and you have a loss function, it's sort of developing these decision boundaries in order to separate the data. So in this case, you can have a cluster of data on the very left, and then at each of these intermediate layers, it's sort of clustering the data differently as it propagates forward. And then finally, what you have is some sort of prediction. So in the end, I have sort of two plots here just to show what at the top, in this final layer, this top is sort of what an untrained final layer would look like, and at the bottom is what I wouldn't say fully trained, but something that's has no more decrease in validation loss. You can sort of see that the red points have been situated on one side of the plot and the greens on another. And it's sort of not a very simple linear decision boundary. It's sort of more complex than that, and that's just because we have the sum weights of the previous hidden layers propagated through. So all in all, we're trying to separate the data in higher order feature space. And this is done through the combination of these linear projections, and the activation functions introduce nonlinearity to these models. So the problem statement. So we can look at advances in deep learnings, and one of the things that we want to do is we know that in deep learning frameworks, we're trying to implement some form of feature extraction. So whether it be looking at time series or whether you're looking at convolutional neural networks when it comes to images, the network itself is extracting the features. And that's because we're sort of letting the domain expertise that's required in order to create the features, we let the model handle those creating the features. So that's in the case of sequences and images are two popular examples. In addition to simple linear projections, the question is, can we incorporate some other information about the learn process during training? Right? So here we have a plot of red and green dots. And when we propagate in the model, we're sort of taking the linear combination of these points and we're propagating it through. And the question is there any sort of other information that we can extract from this high dimensional feature space? In this example, it's just 2 dimensions just for illustration. But if this was a 1,000 dimensional space, the question is, can we extract information about that? And the question is, what characteristics does this topology display? Because in a way, it is sort of like a topology of points, just in higher dimensional feature space. So we propose something called complexity. So the idea about complexity is that we can actually observe and capture these differences in topologies of a trained versus untrained model. So at the top right here, we have an untrained model. Forget the edges connected for a second. But pretty much if we were to know where the red and the blue points are, we know that when we're randomizing the weights when we initialize a model, and then we have the feed forward, and then the activation, where the points lie in a 2-dimensional space, let's just say for illustration purposes, is sort of randomized because the weights haven't been tuned properly in order to separate. So when a model is trained, well, then those clusters, we can visually see those clusters as the model learns whether to set certain activations how to set the activations for certain types of features. And then you sort of see these clusters, and you sort of know they exist in high dimensional feature space. And when you use a feature like TSNE, you can actually visualize them. So generally speaking, trained models have their nodes spread farther apart. And again, the model is learning to separate via non-linear decision boundaries. But the question is, how can we sort of capture this behavior, and can we make use of this behavior as the model is being trained? And the answer is we can sort of do something similar, where we can actually look at the relationship between the content at different scales. And by content, this is sort of, it can be any form of content, just information about the topology. I'll explain how we get more specific, which in this case is the information contained within different subsets of the node away from the center of mass. So just to be clear, when we're sort of measuring the spread of something, you can sort of imagine something that is very clustered together would have low spread, and something that's clustered spread apart would have high spread. So the question is, how would you sort of characterize that? And the idea is that you can do it in one way, and one of the ways that you can do that is sort of you can look at the whole topology, and then you can sort of look at different clusters of nodes away from the center. So with k equals 1, you can sort of consider just the nodes in the middle. At k equals 2, you consider all the nodes within k equals 1 and k equals 2 and k equals 3. And you sort of know that the information contained about the nodes as you spread farther apart tells you a little bit about the topology. So if you were to focus on something that was very clustered together, you'd know that, for example, those distances from the center of mass would be very small as they're all clustered together. But as they're spread farther apart, the distances increase from the center of mass, and then you have high spread. And the idea is that we sort of have this relationship, n sub k approximates r sub k to the d, which is just to say that there forms a power law relationship in looking at these nodes from the cluster as they spread far apart. And sort of this relationship, d sub m in this case, so it's d up here, or d sub m, which is sort of the mass radius or center of mass fractal dimension. There's this log-log relationship between log of a sub k, which is the information, which I would suggest in this implementation we're doing based off of the standard deviation of the nodes from the centroid, the distance, over the log of r sub k, which is the number of nodes under consideration. So there's a power law relationship in the content of the nodes as you consider different scales of the topology from the center outwards, and we can sort of capture this mass radius fractal dimension via this relationship on the right here, where we're just taking the standard deviations in the x and the y dimension, in which case this is sort of just in the two-dimensional representation topology. You're sort of taking the standard deviation. So to go more into it, the center of mass of a topology is pretty much sort of, you can sort of calculate it as the average of the x's and the y's in all different dimensions. And then, as I said in the previous slide, the mass radius fractal dimension is this relationship of taking the standard deviation in the x and y. This is sort of the relationship that you can sort of summarize it as r sub j, where it's just like in all dimensions. And then finally at the bottom is sort of what the full equation would look like, where you're taking the sum of the differences of each point from the center of mass in the x dimension, square it, and you take the 1 over n sub k of just the number of nodes. So this is just a standard deviation calculation. And the point is you're just doing it in the x and y dimension, and that's sort of the compact representation. This is sort of it spread out, listed fully. Right? So you're taking the differences of the nodes from the center of mass squaring, and you're getting an idea of the standard deviation of all the nodes in the x and y dimension. And the thing is, you're not sort of limited on just taking these distances in terms of like a Euclidean distance or Manhattan distance. You can sort of generalize it using the Minkowski distance, where sort of this is just a general representation of for any p, which is sort of order of the norm, whatever p you use. So in the case of Euclidean distance, this would be 2. This expression just is the same thing as Euclidean distance, because you're taking to the power of 1 over p, so this is just the square root, and you're taking the x minus the y's to the p, which is just squaring. So you're doing the same thing as standard deviation. So Minkowski is just a generalized form where you can use any sort of p that you like. So this is sort of the implementation of the mass radius fractal dimension, where everything that I sort of said previously, this is just implemented in code. We're determining the centroid, in this case just to 2 dimensions. And then what you're doing is you're determining the centroid. You're sort of taking the distances of different subsets of nodes away from the center of mass. And then you're sort of determining how many nodes are considered. You're doing the mass radius fractal dimension with the given nodes. And then you're determining the mass radius fractal dimension from this limit, again, which is the log of the number of points. Sorry, that should be the other way. So the log of the information all over the log of the number of points. And then pretty much you just have that log-log relationship at 3 different scales of k. So that would be k equals 1, k equals 2, k equals 3. So you extract that fractal dimension from that log-log plot. That's just the slope. And then you have a fractal dimension for the given topology. And this is just the expression for the mass radius time complexity, which is just mostly due to the requirement of determining the distances of the nodes from the centroid. So there's sort of a sorting algorithm that's required, right? So that's why you sort of get a big O n log base 2 of n, because there's sort of you have to find the distances from the centroid to all the nodes. So then you have to order them in a way. And then all these other expressions here just have to do with trying to find the mean. And then this one down here has to do with running sum. So there's a more compact way of doing it as well. In the full paper, we sort of have the full expression, where k is the number of scales and d is the dimensionality of the topology. So everything here is limited to 2 dimensions, but we can extrapolate this to any d dimensions, and the same sort of computation applies. You can still determine a centroid in d dimensions, and you can determine distances in d dimensions too. Now, secondly, this is just an example of we can actually take the same sort of idea of the mass radius, where we're looking at different scales away from the centroid. The gyration is just the gyration fractal dimension, which is implementing exactly what I just said. The only difference is the radius of gyration actually changes with each k. And that's just because rather than considering a single centroid and it not changing, what happens is depending on the nodes that are considered, the centroid can actually change depending on the nodes. And this just makes it more powerful when you have topologies that aren't nicely clustered symmetrically. So if they're spread out in any sort of other way, the gyration fractal dimension can actually capture that spread much well. So all you're doing actually, compared to the previous slide, is that you're simply recalculating the centroid for each subset of nodes k, and then determine centroid just rather than being at the beginning here, it's just within each n sub k, and you're determining the centroid of the nodes under consideration, everything else being the same. So just for the methodology, as we were trying to test our implementation, we looked at 2 synthetic data sets with different sort of training parameters, just to consider different types of data sets that this can tackle. The number of samples we kept at sort of 5,000 points. And then we sort of played around with different positive classes, where the positive class percentage, let's just say the red nodes here, represented either 1% of the total points or 5%. So that would be like 50 points, or 50 times 5 in the case of 5%. And the dimensionality, we weren't restricted to just 2 dimensions. As you've seen, this is just for illustrative purposes. But the number of dimensions can be 2, it can be 30, it can be 500, right? All the same computation and application of the distance metrics still applies. And we looked at also 2 different sort of, even subtopologies, where we can sort of take a default cluster here on the left, and an anisotropic where sort of the points are just transformed and they're sort of spread far apart. So this is just to test the sensitivity of our complexity measure. So just to go with how we sort of looked at, how we sort of fine-tuned our parameters, our configuration for our fractal dimension approach, there's a few things to consider. One thing being the Minkowski order of the norm, which was that p-value, again, where a p equals 2 is the Euclidean distance, and p equals 1 is the Manhattan distance. The other things we looked at was complexity spread. So one of the things that we did was, so just to go back, we were actually these are just determining the complexity of these default and anisotropic feature sets. So we have the p, we have the complexity measure spread. So what we were sort of doing was, if we wanted to test if our measure was sensitive enough, one of the things we wanted to do was, if we were to consider that previous cluster again, let me go back. Ideally, if we take the the topological complexity of the green points, okay, it would have a certain fractal dimension. And if we took the fractal dimension of the green points and the red points, ideally, other forms of outlier detection, you would expect should be able to detect these red points as outliers. But the thing is, it's not clear just from looking at this if these are all colored the same. So the idea is that the fractal dimension, if it is sensitive enough to the spread, okay, in many dimensions. Ideally, if we consider just the green points, it should have a complexity. And if you mention the green and the red, it should have a complexity. And the farther apart that spread is, the more sensitive the measure is to changes in topology. So this complexity measure spread on the x-axis, in both cases here, is just the spread of the positive and negative minus the negative. Right? So higher spread equates to more sensitivity. So always consider the higher it is, the better. And the other things that we looked at was different k's. Again, these are just spreads. K equals 2 just considers the whole topology into 2 sections, taking the log-log plot of just 2 points. And then k equals 5 just considers 5 subsets of the nodes. And then we looked at the gyration and mass radius fractal dimension. Again, the gyration just being the moving centroid. And what we did was we actually looked at many different forms that the data set can take. But here on the left, we're looking at 30 dimensions with just the default clusters, 5% positive, and then just a second example just to look at with the dimensions of only equal to the anisotropic. So that's exactly what we looked at in the previous slide. This is what the plot looks like in the previous slide with only 1% positive points. So the takeaway I want you to get here is that if we look at the one on the left, at least when it's nicely clustered, at least in 30 dimensions, what we notice is that the lower Minkowski order of the norm tends to perform better. So the Manhattan distance complexity tends to work better. And overall, the gyration fractal dimension being always on the right of the blue dot just indicates that it performed better. There's larger spread. And then, at least in this case, the smaller circles, being lower values of k, actually tend to perform better than the bigger ones of k. And we sort of go into this a little later on, why that might be. And then the plot on the right, this was just to demonstrate that when you're actually having different, most of this might be due to the fact that it's anisotropic. What you sort of tend to see is that it's not clear which sort of subset of parameters of the complexity topology actually work better. So at what values of k perform better, tends to be lower ones tend to perform better as well, but it's not clear at what Minkowski order of the norm is actually optimal for the spread. So we go a little more into this, why this might be the case, but one of the things that we had thought about was, when you're considering many values of k, let's just say, many different values of k. So if we were to just separate this cluster into 5 separate sections from the center going out, what you'll notice is that the red dots really only appear, farther out from the center of the cluster, right? So when you're looking at different values of k from 1 to 5, value of k equals 1, k equals 2, k equals 3, k equals 4, all those k's are considering the green dots, and there isn't much change, right? So for all intents and purposes, it's very similar. But when you actually have k equals 5, then you incorporate information about these red dots, but it's only one of the points that actually matters in the log-log plot, right? So the fact is these red dots are really only being incorporated in the final k when you're considering the nodes farther and farther apart because they're always on the peripheral of these clusters. But at least when you consider k equals 2, right? At least that second k incorporates contains all the information of the red dots, and that changes the log-log plot a lot because you're only considering 2 points in a k equals 2 log-log plot, so it changes the slope a lot, as opposed to k equals 5, it doesn't do it as much. So those are considerations that we had. So other considerations were considered in the full paper, but for the sake of just time and space, we didn't include them. But in general, it seems like the fractal dimension, order of the norm, and some of these other parameters tend to be very topology sensitive. So there's no one size fit all. So we go into sort of what we take with that later on. So the next we wanted to look at is, okay, so we wanted to incorporate the idea of this complexity, but we wanted to do it while the model is training. So one of the things was we actually had sort of a simple feature space. Again, this is just sort of the cluster shown a few slides ago. And we passed it through a multi-layer perceptron, where at each stage we looked at the activations. And then we determined the complexity of the topologies. And we did it in two ways. We determined the complexity of the negative training examples, as I showed in the previous slide, and the negative and the positive, just to see that spread. Again, more spread tells us that the complexity is sensitive to the conditions of the topology. And then these are just sort of the dimensions of the hidden layers. So this is made to be a very small multi-layer perceptron because the feature space in itself is very simple. And then you can sort of see what these intermediate activations sort of look like following feature dimensionality reduction using TSNE. You can sort of say that they cluster very differently. So again, we're just capturing at each stage. So this is sort of what is one plot of many plots that we have shown. I just have two to show. This just goes to show here. This is the linear layer number 1, which is the first linear layer, following linear layer number 2, and then linear layer number 3. So in this previous one, we sort of have 1, 2, and 3. So that's what these correspond to. And then what we did was we determined the fractal complexity of the positive training examples and the negative is just negative. So this positive actually includes, it's just to signify all the points, and the negative excludes the red points. So this was actually implemented as sort of a validation set. So our model is training the points, and then we have a validation set in which in the feed forward, we're capturing the activations, determining the complexity, and then we're plotting them. And then just on the x-axis here, we have training epochs just to show how it changes over time. So one thing to note is that this is a plot that's shown for a feature space here of 2 dimensions only. Of the default form, where it's just the general cluster, not anisotropic, and 5% positive training examples. This is just to demonstrate that it's actually very poor separation at lower dimensionality. So the model is not very good at determining these complexity of these activation layers when the feature dimensions is only 2, right? And that just goes to show that, I'll show in the previous slide, that the usefulness of the measure is determining complexity in high order feature space. It's very efficient at doing so. And we can sort of see that when we increase the input dimensions to 500, again default, and we're only considering 1% positive training examples. So imagine it clusters 5,000 points, only 1% are positive and are very peripheral, right? And they're sort of spread out to a certain extent. And without the color coding of the nodes, it's not very clear that they are an outlier, but the model is actually able to separate them over time as those activations. Again, with 500 feature dimensions, the model is also learning a lot of information about the data set. So it's developing these higher order activation sort of feature topologies as they're trying to separate, developing again these nonlinear decision boundaries. And we can see over time, it tends to be the case that the negative training examples, again with the exclusion of positive, tends to stay very consistent. So that clustering of the activation stays the same, but the model is fine-tuning just the separation of those positive training examples as the model goes on. And at some point it becomes saturated because the model can sort of not learn anymore. That just coincides with a decrease in, this coincides with the fact that there's a decrease in validation loss and training loss, and there's not much more learning to be had. So these become saturated as they converge. But what we notice is that there's great separation at higher dimensionality, indicating the complexity measure is sensitive to small changes in higher order dimensions, which is good. So whether it be outlier detection, whatever it may be, or incorporating in some way into a multi-layer perception, we have quite a sensitive measure that we can incorporate into the learning process. And then finally, we looked at one more thing where we actually wanted to consider the integration of the fractal dimension into the multi-layer perceptron, but we did something differently. We wanted to actually measure the complexity prior to the ReLU activation, which is just sort of the top one here. So we actually determined the fractal dimension of the Z being the net input, and then we added it to the net input, and then we take the activation, ReLU. And then the other thing that we want to consider was post-activation. So we actually took the ReLU of the inputs, take the fractal dimension of the activations, and then added it to the activation. So again, we're just doing pre and post activation. So when we're doing this complexity measure, we're incorporating it by adding it as, the fractal dimension tends to be a scalar. So we're adding that information back in before the ReLU and after, just to see the changes, if anything, to the learning process. So this is sort of a very complicated sort of mapping figure here. The only thing I want you to worry about is that at the top here, what we have is different model configurations. So the model was trained multiple times with different hyperparameters and configurations of the model. Here is just learning rate. Norm just refers to the order of the norm, where there's 3, 2, 1, and 0. So 0 order of the norm doesn't make much sense, but in this case, the 0 order of the norm is actually just the vanilla multi-layer perceptron without any complexity implementation. So this is just the baseline comparison. Gyration just refers to 1 being gyration fractal dimension, 0 being mass radius. Again, gyration being moving centroid, mass radius being stationary centroid. Activation, 1 being post-activation, 0 being pre-activation, and then we have the validation loss and validation accuracy. So that's sort of what this sort of legend is up here, and then we consider different training configurations. So all I want you to focus on is that post-activation implementation. Again, we're just adding the complexity measure to the post-activation post-activation, adding it to the activations. What we noticed was we had higher loss but improved accuracy. So the reason why is because this is sort of a complexity measure that we're just adding on, and it's not being fine-tuned by the model. So what you sort of have in effect is sort of you have this sort of scalar being added, and the model's not fine-tuning it. And then what you sort of have are these exploding gradients because the model wants to sort of depress it, but it sort of can't because you're pretty much just adding a random number. Not a random number, but you're just sort of adding a number without it being thresholded in any way, right? So that's why you have continual loss, because that sort of addition is being propagated through and the loss is high and it can't fine-tune it. So it's not involved in the learning process, so you'd expect high validation loss. But at the same time, you sort of have increased validation accuracy. So while it shows there's 2 models that had high accuracy in this case, actually all of these models here, they're actually in total, I believe it was 18. So there's actually 18 models, but these are all overlapped. So it shows 3 here, but actually there's 18 different models that were trained, and they're just the lines are just being overlapped. So it looks like there's 3, but there's in fact 18 here. But what we noticed was, given that high loss, it actually allowed the model to improve its validation accuracy, as perhaps the model would have otherwise been stuck in maybe a local minima. So that validation loss had the model continually changing the gradients, exploding gradients in this case, because it wasn't being fine-tuned as part of the learning process, but we did find higher accuracy as a result. And then we sort of compared that to whether it be the vanilla implementations or the pre-activation, where we have a more diversity in sort of what the model's outputs were. So the validation lots were much lower, in this case as low as 0.26 or 0.28. So we have lower validation loss, which is good. But the validation accuracy was still stuck at this 0.94. And this is just because there was a few points that had significant overlap with those of the negative training. If you can imagine that cluster, those features just couldn't be non-linearly separable, right? So the validation accuracy just approached this 0.94 because they were clustered too similar to the negative training examples, right? And you don't always get perfect validation accuracy. There's a trade-off between training and sort of validation, right? And trying to decrease both those losses at the same time. But one thing to notice that the pre-activation allowed the model to fine-tune more, and that's just because the recovery of dead neurons. So again, we're using the ReLU activation. So having things pre-activation, what you sort of have is, if any of the net inputs were less than 0, so if any of the Z's, which are the net inputs, are less than 0, again, in the ReLU activation, the output is 0, right? So those become dead neurons. But when you're adding them to the net input, it allows some of the neurons to recover than they would have otherwise, because they would have otherwise been dead. So what that does is allows some neurons to continue learning. So that's why the fine-tuning continued on, as opposed to post-activation. If there was any dead neurons that came out, again, because their net inputs were less than 0, we'll determine the complexity and adding it to something afterwards. Again, the model is not learning because that neuron is dead. So just finally, as sort of, if we can just summarize the conclusions, we considered various data sets, model configuration, and complexity configuration. So we were just looking at different sort of models, different configurations that we can sort of test our complexity approach to see if there's any sort of usefulness that we can apply. We actually looked at different complexity measures and hyperparameters, and what we noticed was a lot of the hyperparameters are sensitive to topology and the order of the norm P. So that just goes to show that there's no one-size-fits-all implementation of this complexity measure, and that most likely we need to, whether it be fine-tune or set it as another hyperparameter, we need to have it, that's something we should have in the back of our mind. And then finally, post-activation, we noticed encouraged training, but led to exploding gradients as it wasn't involved in backpropagation. So this is something we'd have to look at more in the case of ReLU, because yes, you have dead neurons, but at the same time, the output should be 0, but you're adding a complexity measure it. So in some case, you're covering that dead neuron, but it has a constant value, right? Because it's still determining the complexity, but the neuron is dead. So in the backpropagation, it is in a way sort of being involved in learning, but it's now constant. So that's something that we'd have to look at more. And then we noticed post-activation encouraged training led to exploding gradients. And the other things that we wanted to consider, at least in a future application with what we have going forward, is that we can actually allow the model to determine the importance of complexity or ignore it. So if we can consider something like a complexity layer implementation. So now we have the determination of complexity based on the net inputs, W transpose X. Well, we have P, which is the order of the norm, that actually in itself, it could be fine-tuned depending on the model. So we can use that as a something that would require backpropagation, would require a gradient. And then we sort of determine the complexity measure output, and then we can sort of take the dot product with, let's just say, a weight matrix, and then we can sort of add that on to the Z. So in this case, the complexity measure can be implemented in the multilayer perceptron, but we can allow the model to determine whether or not it's useful. If it's not useful, it can set this weight matrix to 0, and then it would in effect ignore it because you would sort of just add it on. There should be an added on here. Or if it wants to incorporate it, it can, right? So this would be very similar to implementation of ResNets or batch norm, where you sort of adding different configurations or highways to your multi-layer perceptron or model, and then you allow the model to determine whether or not there's redundancy in the case of ResNet, or in batch norm, whether or not normalizing the batch is useful or not, and it can set all those to 0 if it needed. So I thank everybody for watching. If you have any questions, you can just correspond with me at this email at the bottom, and I thank everybody for watching.